Regular expressions are a very useful tool and perhaps the most widely used application of regular languages ever. They can be essentially described as a small scripting language for expressing and generating regular languages and their automata. They were introduced by Stefan Kline. We will study regular expressions in two parts. In this first part, we will look at special operators called regular operators on regular languages that give rise to regular expressions. These operators provide a means of compositionally, think moduli, construct automata, and hence prove that languages are regular. The basic regular operators come in four flavors: complement, denoted by a bar over the language; union, concatenation, sometimes also called composition; and Kline star. There are other regular operators, but they can all be defined in terms of these operators. In this lecture, I will define each of these and prove that if the input languages are regular, then the application of the regular operator produces a regular language. This means that the class of regular languages is closed under each of these operations. I'll do this by giving an algorithm for each operator that produces NFAs for their output languages. These output NFAs will be very important in the next lecture on regular expressions. Since every language over an alphabet is a subset of the Kline star of the alphabet, then the Kline star is the universal set. Thus, the complement of a language is every word in the Kline star of its alphabet, here sigma, that's not in L. Now we show that when L is regular, its complement is as well. Suppose we have a regular language L over an alphabet sigma. Then this implies that there is a DFA M that accepts L. We will then build a NFA that accepts the complement of L using the DFA M. To see how we will do this, let's consider an example. Suppose M is the DFA on the top. The complement says that when M accepts a word, its complement, M bar, should reject the same word, and when M bar accepts a word, M should reject the same word. Well, we know that when a DFA accepts a word, it stops in a final state with no input left over. Thus, we know that a DFA rejects a word if it stops in a non-final state with no input. So to obtain the complement of M, we just need to make every final state non-final and every non-final state final. We can now use this intuition to give the formal definition of the complement of M. As in our example, the only thing that changes is the final state. We flip every non-final state to a final state by starting with the set of states and removing all the final states from it. We do this using the local complement, also called set difference. But one question remains. Is the language of M bar the complement of L? Given some word over sigma that is not in L, then M's run function doesn't end with a final state. This implies that the run function for M bar, M's complement, must end in a state other than one of M's final states. However, this is a final state of M bar by definition, and thus W is in the complement of L. Therefore, L bar is accepted by M bar, and L bar is regular. This then gives us our desired result. The complement of a regular language is regular. Union is a bit more interesting than complement. The union of two languages is the set of words in the Kline star that is in either of the languages, possibly both. We can prove that this defines a regular language. We can show that the union is regular by defining an NFA that accepts it. Suppose we have regular languages L1 and L2 over an alphabet sigma. Then this implies that there are DFAs M1 that accepts L1 and M2 that accepts L2. We will then build a NFA that accepts the union of L1 and L2 using the DFAs M1 and M2. To see how we'll do this, let's consider an example. Suppose we have DFAs M1 and M2 on top. Again, if either of these accepts, then we will end in a final state. So to determine if a word is accepted by either of these, we will need to run both of them on the same input word, and we can do this by forking off two threads for each DFA. But this is exactly what epsilon transitions give us. We simply add a new start state that is connected via epsilon transitions to the start states of the original two DFAs. Then every input word will be shipped off to both DFAs, and if one of these accepts, then we accept. Otherwise, if both reject, we reject. This now gives us the intuition we need to define the union formally. Now we have DFAs M1 and M2. To define their union, we build a NFA whose states are the states of M1 and M2, but we add a new state we call Q. This Q cannot be a member of either Q1 or Q2. Then we set our start state to the new state Q. The final states of our new NFA are the final states from both M1 and M2 so that our threads accept when the originals accept. Perhaps the most important part is the transition function. This is where we add our new transitions from our new start state to the original start states. We define our new transition function in terms of the transition functions for M1 and M2. First, we check to see if we are in the new start state and our input symbol is an epsilon. If so, then we return the set containing the two start states of the original DFAs. These are our new epsilon transitions. Then, if we are in our new start state and we are reading a non-epsilon, we return the empty set because we don't want to add any other transitions other than the epsilon transitions to the start states of our DFAs. Now that we are done with the new start state, the rest of our states are either from M1 or from M2. If we are in a state from M1, then we simply ask M1's transition function where to go next. Notice that we wrap the output in a set. This is because we are defining an NFA while the two inputs, M1 and M2, are DFAs. And we do the same for M2. Finally, all other cases return empty set. Now notice that these are all the possible cases that we could find ourselves in when applying our new transition function, and hence this is the complete definition. And again, we have to check to see if this really does accept the union of the languages L1 and L2. Suppose W is in L1 or L2 and hence is in their union. Then by the definition of our new NFA of the union of M1 and M2, running the run function will fork off two threads, one to the start state of M1 and one to the start state of M2. Thus, this implies that our new NFA will accept only if one of the two original DFAs accepts. Thus, our new NFA accepts the union of L1 and L2, showing that their union is indeed regular. Next up is the concatenation of two languages. The concatenation of two languages is the set of every word in the cleaning star that is the juxtaposition of a word in L1 followed by a word in L2. We can show that the concatenation is regular by defining an NFA that accepts it. Suppose we have regular languages L1 and L2 over an alphabet sigma. Then this implies that there are DFAs M1 that accepts L1 and M2 that accepts L2. We will then build a NFA that accepts the concatenation of L1 and L2 using the DFAs M1 and M2. To see how we will do this, let's consider an example. Suppose we have the DFAs M1 and M2 on top. We need to accept a word consisting of a word from L1 and hence is accepted by M1, followed by a word from L2 and hence is accepted by M2. But the NFA who accepts the concatenation should only accept when M1 accepts and then M2 accepts. This tells us that we should first run M1 and then non-deterministically fork off threads that run M2 to see if we can accept the part of the input word from L2. This looks like this. We add epsilon transitions to transitions over to M2 when we are ready to accept the second half of our input word, that is the word W2. We have to add epsilon transitions from every final state in M1 to the start state of M2. Then turn off the final state from M1 because we only want to accept when we get a word that M1 accepts the first part of and M2 accepts the second part of. We only accept when M2 accepts. We can now define the formal definition. Our new NFA has the same states as M1 and M2, but our new start state is M1 start state, so that we always start with the first trying to accept the word in L1. The final states are the final states in M2. This way, we only accept when we're able to consume W1 by M1 and then W2 by M2, finishing off the concatenation. The transition function must be updated to add the new transitions from the final states of M1 to the start state of M2. First, if we find ourselves in M1 and we are not reading an epsilon, then we simply do as M1 does. But if we are in M1 in a final state and reading an epsilon, then we add a transition to the start state of M2. This is where we will move over to accept W2 in the concatenation. If we are in M2 but not writing an epsilon, then we do as M2 does. Finally, in any other condition, we return empty set. This will only fire when A is epsilon, and hence we add no other epsilon transitions. This concludes our formal definition, but does this indeed accept the concatenation of L1 and L2? Suppose W1 is an L1 and W2 is an L2, and hence their concatenation is W1, W2. Then by definition of our new NFA of the concatenation of M1 and M2, running the run function will amount to first running M1 on the first part of the word, and then transitioning to M2 to accept W2. Admittedly, I'm being a bit hand-wavy here, ignoring the fact that the run function will add the final states that delta 1 ends at to the result set, but this gives the idea of how the proof would work. Thus, the concatenation of L1 and L2 is regular. Next up is the clean star of a language. The clean star of a language is the set of every concatenation of the words in L. This includes the 0 concatenation, or the empty word, the 1 concatenations, the words from L, and then the 2 concatenations, which are every concatenation of 2 words from L, and 3 concatenations, and so on. Think of it as the clean star of an alphabet, but instead of single symbols, we are concatenating full words. We can show that the clean star is regular by defining an NFA that accepts it. Suppose we have a regular language L over an alphabet sigma. Then this implies that there is a DFA-M that accepts L. We will then build a NFA that accepts the clean star of L using the DFA-M. To see how we will do this one, let's consider another example. How might we compute the clean star of this DFA? Well, let's think about how concatenation works. After all, the clean star is just the repeated concatenation of the words in L. So 1 concatenated words are just accepted by M. So nothing interesting happens. We will come back to 0 concatenations in a bit. So consider 2 concatenated words. This results in composing M with itself. This means that we connect the final states of the first M with the start state of the second. But notice that 0 prime is technically the start state of M. So what we are doing is connecting the final states of M back to the start state of M. Let's consider 3 concatenations. Again, the first 2 are exactly combined as a 2 concatenation, and then we do another concatenation with that. But this means that we go from the final state 1 prime to the start state 0 prime prime. However, this is telling us that if we merge all 3 of these together into a single NFA, we get one where every final state has an epsilon transition back to the start state. And this lets us get the next word in the concatenation. Thus, the clean star should be equivalent to this. And indeed, it is correct, but it is missing one key group of concatenations, the 0 concatenations. The empty word is always a member of the clean star of a language, but we can see that this isn't true of this NFA. In fact, I would call this the clean plus of a language. That is the non-empty clean star. So how do we add the clean star? Well, perhaps you might think about making the start state final like we do here. After all, this is how we usually accept the empty word. But this breaks the cleaning star. Remember, every word in the cleaning star has to be a concatenation of words from L and nothing else. Well, indeed, the empty word is accepted, but so is the word AB. But this is not accepted by M, nor is it a concatenation of words from L, because B is not accepted by M. So this NFA is too general. To fix it, we simply add a new start state and transition on an epsilon to the original start state. Nothing else changes. So we get this correct NFA for the cleaning star of M. So every final state goes back to the original start state, and we add a new start state that is final and transitions on an epsilon to the original start state. Let's take a look at the formal definition. Our new NFA has the same states as M with an additional new state called Q, where Q is not already a member of M's set of states. Our start state is our new state Q. The final states consists of the original final states with the addition of the new start state being final. Similarly to the other regular operators, we must update the transition function with new transitions. In the case where the input state is the new start state, we add a transition to the original start state on an epsilon. We also add an epsilon transition from each final state from M to M's start state. Next, if we are in some state and not writing an epsilon, then we simply ask M where to go next. Finally, no other inputs produce a transition. The definition of the cleaning star is in terms of concatenation so that we know it is indeed regular. The run function for our new NFA essentially repeatedly calls M's transition function on each part of the input word. If the last call accepts, then we accept, otherwise we reject. And this concludes the lecture on regular operators. We will see more examples in class, and then in the next lecture, we will see how regular operators lead to regular expressions.